Good afternoon, everyone, and welcome to AEC's latest installment of AEC Tech Webinars. I'm Lissa Jersenko, Executive Assistant and Membership Coordinator for the Council. Our session today is External Factors, and our presenters are Paul Robbins and Ken Chien of Castool Tooling Systems. All your computer audio and telephone lines are muted, and if you have any questions during the webinar, just select Q&A from your toolbar and type your question in. We will hold them until the end of the presentation, and our presenters will be able to address your questions then. If we run out of time, Paul or Ken will be happy to take your questions after the webinar. You can get in touch with them directly or send your questions to me, and I will forward them to Paul and Ken. I'd like to tell you a little bit about our presenters. The son of a leading Toronto die maker, Paul Robbins received his postgraduate degree from the Schulich School of Business. He's worked in the light metal extrusion industry for more than 25 years, and he holds more than 20 international patents. As General Manager of Castool, Paul has played a very important role in some of the most influential development work in the industry. Today, Castool Tooling Systems hosts complete tooling systems for extruding light metal. Paul is well known for all of the articles he's authored and for the many technical papers he has presented over the years. The most well-known phrase he's famous for is temperature, 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 from his article Super Extruders, published in 1997 in an edition of Light Metal Age. He's a committed advocate of the view that extrusion is a holistic process, and therefore components of the production system should never be considered in isolation, but always as an interconnected part of the whole system. His website blogs continue to portray his views and visions of this ever-developing industry. Ken is the product director in Castool Tooling Systems, and prior to joining Castool, Ken spent 8 years doing research at the University of Toronto. Coming from a material science and metallurgical background about steel and aluminum, he's been working on optimizing the aluminum extrusion tooling. He also has a dual role as Asia sales manager and has been visiting customers worldwide to gain a broader and deeper understanding of products and their performance. This unique dual role enables him to understand feedback from customers directly and improve tooling. Both of these gentlemen have been very important contributors to ET events and have published papers in many of the ET proceedings. And now it gives me great pleasure to welcome Paul Robbins and Ken Chien.
Well, thank you very much, and it's a beautiful day in Toronto, Ontario anyways, hopefully where you are as well. Hey, Ken.
Yes, it's nice weather outside.
One of the biggest factors is, I guess external factors could mean many things, but being a member of the die committee, we look at external factors, meaning everything but the die. So it's those things outside of the die that affects the die performance. The goal for every extruder should be maximum ram speed, or speed, maximum recovery, which is minimizing our scrap, and maximum time utilization. These are really the only three variables that we have as extruders to allow us to make money. I visit a lot of extruders, and I must admit in most cases I spend a few minutes just looking at the economics of extruding and how we make money. Unless, you know, I get several extruders, in fact maybe 50% of extruders that I visit that don't measure ram speed. And I guess I can understand not measuring speed if you're not in a race, or maybe you're not busy so you have time to waste, but it really isn't a situation that we want to be in. If you're a race car driver and you don't care about the speed of your vehicle, you shouldn't be racing. And I think without measuring ram speed or being aware of ram speed, it's very difficult to be taken seriously as an extruder today. One of the problems with die correction is that die correctors typically choke bearings, or anything the die corrector does typically slows ram speed down. As soon as the die corrector touches a port, touches a bearing, typically they reduce the die life and also reduce recovery. So unless necessary, which meaning unless the die was made incorrectly, die correction should be minimized. And we should focus on the external factors to control speed through the die versus trying to modify the die to work in an imperfect environment. One of the problems with external factors is we have, I believe, 40 minutes, right?
Yeah.
We have 40 minutes, and we reduced this presentation to 41 slides. So I don't know if we're going to actually finish it. Chris Jowett from Rio Tinto and Danny Dunn helped us prepare the slides, and we were actually reducing slides up until about 3 minutes ago, so we could hopefully finish this in 40 minutes. One of the first things we want to look at is the billet. The alloy affects how things work, the quality of the billet, and also the temperature of the billet. When we're looking at die heating, we'd like the die to be plus or minus 10 degrees Fahrenheit from billet temperature. So if you have an 860-degree billet, you would like the die to be somewhere between 850 to 870 for the first push. The container, we want the bore of the container to be round. If the bore isn't round and say is bellied, we're going to collect surface of the billet in those areas, and it's going to affect surface quality. Also, unless the container is concentric or round, it's impossible to run a dummy block with any sort of consistency. The temperature of the container also matters, because the temperature of the liner affects the way the billet flows into the die and also affects die temperature. Support tooling that supports the die. If the support tooling is inadequate, the die is able to flex, which will in turn flex the bearings, which will affect the speed of the alloy through the aperture. Press alignment, and by press alignment we mean stem to container alignment and also container to die alignment. The shear blade, we want it to cleanly and completely remove aluminum from the die face without pulling any material from the die. And we would like to do this with minimal or no lubrication. Which brings us to lubrication. We would like the least amount possible, and we want the type to be environmentally friendly and also extrusion or profile friendly. Ken, you can talk about billets.
So the choice of the billets, it depends on the application that you would like to use. So the application is, what determines the application is the wall thickness, the corrosion environment or ductility of the part that you want to extrude. So that will determine what kind of alloys, 1000, 3000, 6000, or 7000 series alloys. And for the billet, here are just a quick samples of alloys. For 3000 series alloys, a lot of people they extrude microtubules will need to use 3000 series alloys because of the wall thickness they are dictated to. And for 6000 series, which is more general application, you extrude a lot of it for windows and doors, is you get the maximum, or it's, how do you want to call it? It's very easy to extrude the 6000 series alloys. And for some high-strength applications, you will look for 7000 series alloys for aerospace and automotives. But there is a minimum wall you can extrude through that 7000 series alloy as well. So it all depends on applications, then it will determine the alloys you should use.
Okay, a couple other things that come in this is the length of the billet. It's not only the alloy of the billet, but also the length. And the length very often is dependent on the table size, extrusion ratio, and the finish size of your actual extrusions that you're selling to your customers so we get the best recovery. Whether the billet is cut or sheared, we would like to avoid shears for the most, but unfortunately probably more than 50% of the extruders today have billet shears. The problem with sheared billet is typically there's deformation on both the front and the back of the billet, which affect mainly air entrapment once it's being upset. Also the use of one or two piece billets. Also whether the billet is primary or secondary. The casting method of the billet affects the amount of inverse segregation on the outside of the billet. Homogenization. I hate to say it, but I was actually at an extruder 2 weeks ago who chose not to homogenize their billet. You know, in so doing, they overheated the billet in their billet oven and left it longer on their transveyor so the billet would have a chance to cool so they could avoid homogenization. Unfortunately, this isn't really a good way to save money or time. They had very little control over the billet temperature, and I would say very little control over the finished product. Billet surface quality, again, which is affected by the casting method and homogenization, and the temperature of the billet, both the accuracy of the temperature and uniformity, whether it's uniform or tapered in temperature from front to back. One quick thing I'd just like to touch. What most extruders realize that, you know, if you're extruding 6000 series alloy and you have a customer that wants to extrude a 10 thou wall or probably a 9 thou wall, it's impossible to extrude that size of wall with 6000, which takes us to maybe a 3000 or 1000 series alloy, which has a lower flow stress, which will allow us to extrude a thinner wall. Ourselves as tooling vendors, the thickness or the aperture between the dummy block and the container wall is very similar to the aperture in the die. So when we go from a 6000 series to a 3000 series alloy, and we reduce our minimum wall thickness from maybe 25 thou to 10 thou, the critical gap between the dummy block and the container wall also changes. So getting a dummy block and liner to operate together as a set is much more difficult when you go to softer alloys.
So the graph shows that if you look at a graph, you have all sorts of different alloys from 1000, 3000, up to 7000. And on the bottom of it is a flow stress. You can see 7000 series alloys has a very high flow stress. So you need a very high pressure to push them around. And then they will not like to go through small spacings. That's why there's a minimum wall thickness for the 7000 series alloys. And if you look at the other end, look at the green one, you have 1050, you have 1000 series alloys. The flow stress of that is almost 10 times or 5 times smaller, less than a 7000 series alloys. So that's why it's very easy to extrude, and then extrudability is higher on that end. So this graph shows you the trend from soft alloy 1000 to hard alloy 7000 series alloy, and their flow stress and their extrudability relationships.
You're better at that than I am. Billet homogenization, we won't take much time on it because I'm sure that most extruders do homogenize. But if we want to evenly distribute alloy elements, again, Ken has his PhD in metallurgy, and he'd probably speak better at this than myself.
So the alloy you have is not pure aluminum. You have all sorts of different elements inside. And what you wanted to do is you want to nicely dissolve those elements into your aluminum. So you need to evenly distribute the elements into it, and then you need to give it time and temperature, which we call homogenization. What happens when you don't do it is you don't have a uniform property of the alloy, and you have an inferior surface. And usually on the surface it has high iron content, and it would like to pick up, and because of high iron content, and because of different uniformity or different property on the surface of the billet and the core of the billet, there's a strength difference during extrusion, and then you would like to, what happens is, and it would be premature tearing at low speed, and you just cannot get the high strength and high hardness through a non-uniform alloy. So at the end of the day, if you don't homogenize it, you are going to lose the productivity for sure. No matter how you do it, you don't have a good product to start with, you're going to lose your productivity.
So whatever our extruder from 2 weeks ago hoped to save through not homogenizing, he was definitely losing on both ram speed and recovery. Accuracy of billet temperature. The billet temperature has to be within plus or minus 10 degrees of our target. I think in today's world and capabilities of equipment, there's no excuse for not having a billet that's within 10 degrees of our target. I don't think I need to go through any more, but as the billet becomes colder, it's harder to extrude because the flow stress of the billet increases. If we want to optimize our speed, our ram speed, we have to have control over billet temperature. Billet taper heating. I think the goal of every extruder is isothermal extrusion. By isothermal extrusion, it means that we would like to have an optimum and stable exit temperature from the extrusion press. If we start with a uniform heated billet, the only way to get a stable and uniform exit temperature is by varying our ram speed. If we vary our ram speed very much, we're also going to be changing the direction of the die and also the opening in the aperture, which is going to change our shape and wall thickness and speed of aluminum flow through the die. So it's virtually impossible today to have isothermal extrusion 100% ram speed. So the only other way to do it is to taper heat the billet. And I just saw we just did it in Celsius instead of Kelvin. Most of the new presses offered today offer a maximum of 100 degrees Fahrenheit taper in a billet, or 50 degrees Celsius. The reality is to attain isothermal extrusion today, we're looking at tapers anywhere from 100 to up to 300 degrees Fahrenheit. And I would say 300 degrees is extreme, but there are extruders today using up to a 300 degree taper on the billet. The goal by having a taper in the billet is to have minimal, if any, variation in ram speed, to have a relatively consistent ram speed and a consistent exit temperature. Die heating, we would like to have the die plus or minus 10 degrees Fahrenheit from the billet temperature for the first push. If the die is colder than the billet, it means that you're going to increase the stress on the die and create scrap. Because aluminum is quite, or the flow stress of aluminum is quite sensitive to temperature, if you decrease the temperature of the alloy or the die by 10 degrees Fahrenheit, you increase or decrease the rate of flow by about 1%. So if the die is 50 degrees Fahrenheit below billet temperature, you're going to be increasing the stress on the die by about 5%. So temperature matters. On the other side, if the die is inconsistent from top to bottom or left to right, the flow rate through the die will be different, which means that the shape and wall thickness will also be distorted from what we want. We know that H13 or 2344 anneals at about 1,085 degrees Fahrenheit, and we know that the nitride layer on the die bearing starts to degrade about 1,098 degrees. So when we're heating the die, we want to make sure that we never go above these temperatures. We also know that the longer the die is left at temperature, the more oxidation we get on the bearing, which causes deterioration in surface quality of your profile. So we would like to limit the time the die is at temperature to as short as possible. In best practices today, it's 8 hours, which means that the die can only stay in a die oven for 8 hours, after which time it comes out of the oven, goes back to the die shop for polishing, and then comes back out for extrusion again. Unfortunately, more than 50% of the global extruders today still use chest ovens. And the reality is, to heat a die in a chest oven, we have very little, if any, control over temperature. And the majority of these dies are left at temperature for too long, causing oxidation and surface finish problems. This is just a quick look at a die that's been in a die oven for more than 8 hours. And you can see through the microscope that it's caused oxidation on the die bearing and die lines on the profile. Single cell die ovens today, I think, are accepted as the best way to heat a die. We get 100% control over die temperature without overheating the die, and can more or less guarantee that the die will be plus or minus 10 degrees or 5 degrees Celsius from billet temperature. It also allows us to control time at temperature, even in cases where we have dies that are 35 to 40 inches in diameter. Today we can heat them in somewhere about 5 to 6 hours, which still gives us time to extrude.
So we just reviewed that the temperature in extrusion is always changing, and what the temperature will do to your flow stress, you can see from this graph, that when the temperature is colder, for the same alloy that you're extruding, the flow stress is going to increase. And then you can see the scale that every 20 degrees Celsius or 40 degrees Fahrenheit drop in temperature, it's about 10% of flow stress increase. So imagine that if you don't control your temperature, the flow stress of your alloy in the same die, in different cavity, different pore holes, will be different. And that's going to create a lot of problems. And also, it will create a problem in the profile and thickness as well.
Next, containers. Really, the only part of the container that affects extrusion is the liner. And we would like the liner to be about 50 to 100 degrees less than your billet temperature. And this gives us the ability that can control the flow of the surface of the billet into the die. As the liner temperature starts approaching billet temperature, the flow of the inverse segregation or oxide layer on the outside of the billet will start flowing very freely into your die. If it was possible to have the liner too cold, maybe 200 degrees below billet temperature, we could actually pull the surface of the die or of the billet back and have something called coring or type B inflow. We also want the liner to be round. If the liner is bellied in any way whatsoever, we're going to get a collection of billet surface and oxides on the inside of the liner, which will be released into your profile at random, causing surface finish problems, non-metallic inclusions, and also mechanical inconsistencies in your product. We also need the liner to be concentric to allow the dummy block to work. If the liner isn't round, it's impossible to have a dummy block operate efficiently. The liner temperature also affects the die. If we use containers with external heating, typically the top of the container will be anywhere from 50 to 100 degrees hotter than the bottom of the container. This is because heat is being leached out of the bottom of the container into the container housing, and heat is rising within the container and the container housing, making the top of the container hotter than the bottom. If this is the case, once you have conduction between the liner seal face and the die, the top of the die will become hotter than the bottom of the die. The flow stress of alloy going through the alloy at the top of the profile versus the bottom of the profile will be less, and we'll have more flow, which is going to cost us inconsistent shape and also wall thickness.
So the key for the container is the thermal stability of the container, not the thermal or temperature uniformity. So we've discussed a lot about temperatures, and the temperature of the liner will have very dramatic effect on the skin of the billet flow. So if the liner is hotter than the billet, what will happen is you will have a type A inflow. So if the temperature of the liner is colder than the billet, what will happen is you will have a type B inflow. What's more interesting is when I go to extruders and ask, do you know what is your liner temperature? They, most of the time, or 95% of the time, they do not know. They only know the reading from the thermocouples. So anything can happen in their container because the container temperature or liner temperature is not stable.
Well, and typically when we look at the thermocouple reading, it only tells us the minimum temperature. So if you set the thermocouple in your container at say 800 or 820 degrees below billet temperature, which may be 860 degrees, the only thing that thermocouple does is turn the heaters on when the container is less than 800 or 820 degrees. There's no control whatsoever at the temperature above that.
And what's interesting, there are actually a better way to control the temperature of the container or temperature of the liner. The only thing you have to rely on is look at this simple physics formula. Look at the heat coming in from the billet, heat generated through the deformation of the extrusion, and heat going into the extrusion profile or going to the die. The rest of it should go to the container. And what this formula tells you is there are only three things that's more important, which is temperature gradient, conductivity of the material you're going to use, the container material, and how much surface you allow the heat to flow. When you look around, or maybe look at your press, take a look at your container designs. Typically, there are three different container designs. If you look at on your left, you have a heater from the outside provide heat to the container. We call it design 1. Or you can have heater which you insert usually in the center of the mass of a container. We call it mixed section or design 2. Or we think it's a better way that you should provide heat or temperature to the most important part, which is liner. We move heater close to the liner, which is QR container, or we call it design 3. We did a simulation on this 3 different designs, and the graph shows which is the first factors that control the temperature extraction or temperature stability in the container, temperature gradients. And you can see number 1, the gradients start from positive to negative about 100 billets. So that means the gradient is changing all the time. Design number 2, there's a big fluctuation for every 15 billets or so. Design number 3, when you move the heater close to the liner, it's very, very stable. And if you pick the right steel for the container, in this case, we would like to see the steel that's being used has high thermal conductivity coupled with high toughness. And so the choice comes down to AISI 4340 steel. It has 60 megapascal of fracture toughness and 42 watts per meters per Kelvin for thermal conductivity. That is almost doubled of thermal conductivity of typical material I use or we see in the market, H13 or 1.2344, and also double the toughness of 1.2344 or H13 materials. When you combine these two, thermal temperature gradient and the thermal conductivity, you see right away which one is the winner. The red one, or the one design number 3. It has a very consistent heat dissipation rate compared to design number 1. When you heat it from externally, and it fluctuates from positive to negative. And the other one, design number 2, it fluctuates and has about half of the capacity to dissipate heat. What we want is the temperature of the liner to be controlled. So if you start with the uniform container, there's no place for heat to go. So you cannot control the temperature because you do not have a temperature gradient. And we want there's a temperature gradient, high thermal conductivity, and when it is necessary, we will provide surface for the heat to flow. And when we look at the construction of the container, how strong or the integrity of the container, typically people will say I will have 2-piece container, or sometimes I will have 3-piece container, but the reason behind it is not clear. I think the reason behind this 2-3 pieces is because it depends on the extrusion pressure. You can look at this graph. It shows that if you don't have anything, don't do anything to it, it's just thick cylinder, and you apply 120,000 psi dummy block phase pressure. The pressure you see on the liner is going to be about 216,000 or 216,000 psi, but you can reduce that pressure when you add another liner to provide interference shrink fit to it, reduced by about 25%. You can reduce a further 20% to from the pressure when you have a subliner into it.
So the biggest factors here are pressure and also length of the container. Today, containers are getting much longer. In these long containers, we typically go with a 3-piece liner so we can control the deformation or mechanical expansion of the liner, or when we're in high pressure. Very often today when we go to long billets, we also go to high pressure. And the combination of high pressure and long billets means we have to have 3-piece containers.
Yes. So remember we're talking about when you need supplementary cooling, and now you have a choice to where to put the additional surface for air cooling. Sometimes we see people like to drill holes in the container, which is a very bad choice because you provide the container some stress riser at a high stress areas. If you really need the cooling, extra cooling, the choice is put it on OD, because OD of the container has low stress during extrusion and it has higher surface area. If you pick the same size container, simply move the cooling hole, cooling channel from liner to OD, you would quadruple or increase 4 times the surface area. But then you will need to use high thermal conductivity steel to conduct heat away from liner to the surface.
Typically, this is only done with microtubing, or in some cases, some 7000 series alloy extrusion. Dummy blocks. Typically, the clearance at room temperature between a dummy block and a liner is anywhere from 35 to 60 thou on diameter. The majority of dummy blocks in the market, or fixed dummy blocks in the market today, expand anywhere from 25 thou to 40 thou on diameter. What we focus on is the billet skin thickness that's generated during extrusion. So we don't want to run steel on steel, and we don't want to extrude by the dummy block, between the dummy block and the liner. But we would like to manage the skin thickness somewhere between 8 to 12 thou. If you want to look at an 8-inch diameter billet by 40 inches long, the actual skin weight should be somewhere around 400 grams or 1 pound, right? Yeah. The biggest problem with dummy blocks is plastic deformation or creep. We would like the dummy block to expand to the 25 to 40 thou and come back to as close as nominal for as many times as possible. And by doing this, then you can extend the life. One of the biggest problems in dummy blocks today is container liner concentricity. If your liner is bellied, your dummy block life is going to be minimal. If your liner is overexpanding so that you have high pressure or a very long billet, you have to make these containers typically in 3 pieces to manage the mechanical expansion of the liner at temperature.
Yep.
Okay. Function of a dummy block. I think I went through this pretty good. Let's go to the next one. Just one caution. We're running into billets up to 60 to 65 inches in length today. As the length of the billet is increased, to maintain breakthrough pressure on the die, we're seeing pressures increased from anywhere from 10 to 20% from what we used to see. And in these cases, the face pressure on the dummy block and also the container is above what dummy blocks and containers are typically capable of. If we take a dummy block that can function properly at 100,000 psi, increase the length of the billet by 10 to 20 inches, increase the pressure by 10 to 15%, the dummy block will fail. And by fail, we mean plastically deform. There are some dummy blocks on the market today, both European and North American, which are capable of functioning at the higher pressures. And in these cases, you need to look at a high-pressure container and also a high-pressure dummy block. Cleanup blocks, number 1, if you don't use a cleanup block, you have a problem. And if you use a cleanup block and nothing comes out of the liner, that no skin is left, you also have a problem. We want the dummy block to leave a skin on the liner somewhere 8 to 12 thou. And if the liner is anywhere from 50 to 100 degrees Fahrenheit less than your billet temperature, between the liner being colder and the difference in expanded diameter between the dummy block and the liner will allow the skin thickness. If you don't have this skin thickness, you're going to be getting surface defects on your profiles and blisters definitely in the back of your billet or profile. With best practices today, we typically have 2 cleanup blocks per press. The press operator has 1 cleanup block that he uses each time he changes alloys, and the other cleanup block is typically in the hands of the die corrector, which is used 1 time per day, usually first thing in the morning. When the die shop runs the cleanup block, the first thing he does is he doesn't use the butt shear on the last die prior to running the cleanup block. That die is taken off. Once it cools, he measures the OD of the die or the die ring to the butt to see the concentricity or alignment between the container and the die. Next, he runs the cleanup block and visually looks at the skull that's removed on the front of the block. If it's a tiara, which means it's skewed to one side, he understands that the stem, the container alignment isn't accurate. If it's concentric and nicely formed, then he knows that the stem, the container alignment is quite good. Then he'll weigh the skull removed from the liner, and again on a 8-inch diameter billet by 40 inches long, we would like to see about a pound of skull removed. If the weight is above this, typically it means that the liner is bellied and we're entrapping more aluminum than we want. If the weight is less than this, typically the dummy block is plastically deforming and we're leaving inadequate skin thickness on the liner.
And through the practice of dummy cold cleanup block, you can see the press alignment. And the picture that you see is because of inadequate pressure alignment. It's
horrible.
Horrible, not just inadequate.
The problem in poor alignment is you're going to get speed differences in multi-cavity dies, which means the run out from one side won't be uniform with the other. We're going to get flow differences into the shape. We're going to get inflow or something that looks very much like the liner is too hot. Alignment also causes this. Today we'd like to keep alignment, I would say 60 thou is being kind, 40 thou is probably better. And by 40 thou alignment, we mean 40 thou at temperature. And again, alignment should never be taken with a cold tooling stack, cold container, etc. It needs to be at operating temperatures. And again, we have 40 thou here instead of 60, which I prefer. You can see in the thermal image on the right-hand side that in this case, the container housing is hot, and the top of the container housing is about 100 degrees hotter than the bottom. So we have a lot of things going on here that we hope not to see. The problem with the container housing is it's big.
And it's made of metal, and the metal can expand at high temperature. So if you don't control the temperature of the container housing, it moves around by its own will. Because at the start of extrusion and at the end of extrusion, it just moves around. And then you quite easily look at the thermal expansion coefficient and look at your container and assume that, for example, that we saw from the thermal imaging, from the top of container is hotter than the bottom of container, and look at your container, and then you will see how much your container is moving if you don't control the container temperature.
And if you're using external heating elements on your container and you're only extruding 5 or 6 days a week, which means on Sunday that those external heating elements are running at anywhere between 1,000 to 1,300 degrees Fahrenheit to maintain your container at 820, the container housing on Monday morning is going to be more than 800 degrees. And if you run 24 hours a day until Friday, by Friday afternoon your container housing will typically be maybe 300 degrees Fahrenheit. If we change the container housing temperature by 3, you have no chance whatsoever of maintaining your alignment within 40, 60, or 80 thou. We just want to touch quickly on support tooling. Support tooling needs to be adequate for the alloy and size of die and pressure that you're extruding at. If the support tooling is not flat, controlled as far as tolerance and size, you will get deflection in the die.
This is a simulation you see from the feeder to the die, backer, and bolster and support tooling. The deformation is there. And so if you don't have a good support of the tool stack, the dimensions of your profile is going to be different. It's going to change it all the time.
And if the aperture is deflecting, your bearing is going to be losing control. You're going to be extruding at a faster rate of speed than you'd like to. You're possibly going to get pickup and shape variation. Shear blade design also matters. Typically, there's maybe 4 different types of shear blades. We can run scoops, we can run blunts, we can run knife shapes, and some of us run a delta shape as well. The first thing we look at is the thickness of the butt, whether it's, say, less than an inch, between 1 to 3 inches, or over 3 inches. And typically this is driven by the structural integrity of the profiles that you're extruding. It also is affected by the container of your liner, or the temperature of your liner. If your liner is too hot, you're going to be collecting a lot more oxides in your butt, and hopefully you're running a thicker butt, because they have to go somewhere. What we want to do is have a clear cut and a complete cut on the die face without pulling any aluminum whatsoever from the ports. If we pull alloy out of the ports and we have air gaps in these, the next billet that comes in will create blisters in these areas. And typically, when your butt shear isn't working well, people are also adding a lot of graphite lubrication. Air plus oil or graphite makes explosions, and again, we lose the structural integrity in our profile. These are just three shapes here. On the top left, we have a scoop, which we can use for relatively thin butts, usually 6000 series alloys. On the right is more of something we'd use for a 7000 or 5000 series alloy, which is relatively blunt. Lubrication, if we go back maybe 20, 30 years ago, we started with graphite, then we tend to move into acetylene, then we moved into powdered boron nitride, then we moved into liquid boron nitride, and today the preferred lubricant is soap. Soap is relatively inexpensive, it's user-friendly, it's environmental, and it has very little, if any, effect on the profile. The good news is that the wetting surface is about 1100 degrees, which means when we apply it to the die, to the seal face, to the billet, or the butt shear, we get no smoking or no dripping. Thank you very much. I think we've actually got our 41 slides in 40 minutes. Thank you.
Thank you so much, Paul. That was a great presentation. Any questions? Sorry, I have an echo going. Okay, we did record tape, and it will be available on later today or tomorrow. Paul and Ken, can you give me
Sorry?
Can you mute your phone? I think the echo may be bouncing back from your phone. Okay, sorry about that. We will also be sending out an evaluation survey later today or tomorrow, and we ask that all of you share your comments and ideas with us. We do value your input. It's very helpful when we're planning future webinars and face-to-face programming. And we encourage you to visit aecmeets.org quite often for updated information on our events. We will be having 2 webinars in July. And July 13th will be ASTM compliance for 6000 series aluminum extruders. And that will be presented by Greg Lee of Hydro. On July 29th, Randy Kissel will present the 2015 Aluminum Design Manual. Both of these are open for registration, and you can find the information on the AEC website. Also, most of you, I believe, have gotten the recent AEC meets, so the registration link is also in that publication. And mark your calendars for the Fall Management Conference, which will be held in Washington, D.C., September 26th through the 28th at the Grand Hyatt, Washington. And we're also going to have a process optimization workshop in Rosemont, Illinois, near O'Hare Airport, and that's scheduled for October 25th and 26th. We hope to have registration open for both of these events later this summer. And the links for online hotel reservations are live, and you can also find those on the AEC Meets site. Okay, do we have any questions? Okay, Paul and Ken, go ahead and unmute your phone. Our first question is, how often should containers be changed out for a 24-hour, 7-day-a-week operation?
Typically, because it's surface finished, so if your dummy block appears running relatively clean and your surface finish on your alloys are acceptable, today I would say standard liner life is anywhere from 12 to 18 months.
We've got a few more minutes, so if anyone else has any questions, our presenters are ready to answer. Okay, we do have another question. What is the most likely cause or causes of inclusions in 364 alloy?
Or 63? Or 364?
I'm not sure what 364 alloy is, sorry. But, you know, we're working closely with Chris Jowett, and we can always respond to that after if someone wants to send us an email, and we can give an accurate answer back again.
Oh, he meant 6463.
Oh, that's easier.
Where's
You can ask.
question, just to ask a question to a question. Where is this showing up? Is it showing up post anodizing, or is it showing up on the table itself? Did you get that, Lisa?
Yeah, I'm not quite sure. This is post ano, not seen on table.
Okay, so it's happening afterwards. Typically, what we would do is go back to start, first of all, with the release agent or the lubricant that's being used. If they're using a graphite-based or an oil-based material, the problem with that is that there's too much residue on that and it's not cleaned out, even with some of the best chemicals that are used in pre-wash of anodizing. Second of all, if it's a hard inclusion, I would go back to the dummy block and the container interface, either sizing on the block, clearance on the block, temperature on the container, but the interface between the dummy block and the container is allowing too much billet skin to be extruded, which is showing up later after anodizing. So a two-part answer would be A, review the type and the amount of lubricant being used or release agent being used. B would be the interface between the dummy block and the stem and the billet skin that's being left in. So a properly functioning cleanout block would lead you down the road whether or not that interaction between those two parts is correct.
Okay, we've got a couple more minutes. If anyone else has questions. Okay, well, you must have been very thorough.
There you go.
Hopefully. Or too general, one or the other.
Well, once again, I'd like to thank you very much for your participation and your presentation from Castool. I'd like to thank all of the attendees today for joining us, and we hope to see you in July for the next webinar. On that note,
have a great day. Thank you very much.
Thank you. We'll talk to you soon.
Bye-bye.
Bye-bye.
Bye, everyone.